Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
University of Illinois at Chicago. And I'm a Master of Science candidate there, working on my CS degree. And I'll be talking about this device today called the LambdaTable. To start with, let's imagine, bear with me here for a second, let's imagine that we are all researchers at the National Center for Microscopy and Imaging Research. And our job is to figure out how the human brain works. And the way we're going to do that is we've got at our disposal terabytes of basically what we're looking at here, which is rat brain imagery. And these images are taken from a very high-powered microscope. They take these small scans of about 4K by 4K and tile them together to create sometimes on the order of hundreds of gigabyte data sets. You can see sort of a zoom in here on the left and start to see some of the context that it's in there on the right image. And what we want to do is we not only want to just look at this data, but we need to do some work. We need to work with this data to start to understand how different images correlate with each other, to try and look at some patterns, and to make annotations and also share this information with our colleagues. Though we do have some nice technology like this display to visualize it, when it comes to doing that interactive work, we're basically stuck with our desktop PC, monitor, and a mouse. Let's give one more example quickly. Here's, let's say we're geoscientists now working with the Joint Oceanography Institutes, and we have core data. A core is basically a big cylinder of Earth that was pulled out from the bottom of the ocean. And they're about 1 meter long, and they're scanned. They're split in half and scanned with a very high resolution scanner, which gives us about 1,200 dots per inch. And there are about 300 kilometers of this data out there. And once again, we want to go through and look through different cores. You can see here that it's sort of like a layered history of a certain spot on the Earth. So we need to be able to look through these different cores and start to look at correlations between different cores at different sites, and once again be able to display metadata right there next to the core and make annotations and generally manipulate this data. And the tools right now for manipulating them are just not up to the par for this task. So the challenge that I'm working on, and some of us at CVL are working on, is to facilitate this type of group work with these very large data sets. And once again, this isn't just looking at them, but actually being able to interact with this data. Our approach is to take the knowledge that's already out there in terms of tangible user interfaces, the research that's been done on table interaction and co-present collaboration, and apply it to some technology that we've been working on, which includes these tiled displays and high-speed optical networking. And what we've built is an interactive tiled LCD visualization table. It supports visualization by providing a very large, high-resolution display surface, by powering that display surface with a cluster of computers, and by fueling it with this optical networking research that we've been engaging in. In fact, as a side note, the term LambdaTable refers to the scheduled lambdas that we're able to bring into this display device, which allows us to access very large data sets remotely. In addition to that, this table supports interaction by providing a common display surface for a group of users, multiple user interfaces, and tangible user interfaces. So clearly we're not the first to be engaging in table research. In fact, the high-space table, of course, we just heard about. However, one common thread that we've seen in most of these table devices is that they generally use a single projector. And those projector resolutions are generally lower than 1200 by 1600, which for the kind of data we're working on does provide some limitations. And there's that center tile is 1200 by 1600, and you can see at full resolution that's just going to give us a small segment of the data that we're trying to work with. This is an image of the Lambda table as it stands now, just to sort of show you the parts here. You can see that it's got two cameras right now. We've got 15 LCD tiles, giving us a total of 8,000 by 3,600 pixels. We have the tangible user interface is on the surface of the table, and there's an IR pass filter on both of the cameras. The interface device uses, right now it uses infrared LEDs to provide a pattern that's tracked by the tracking system. And the table is spacious. It can fit up to 15 people around it. The tracking system right now, once again, the devices are marked with IR LEDs, and we're also looking at researching using reflective material to create a pattern and illuminating them with an IR illuminator. It's a pretty simple 2D pattern matching problem. We can do any number of distinct patterns matched, tracked on the table at one time, and it tracks both the position and rotation of the devices. And up there on the far side is a picture of the current prototype mouse device, and that device also registers left and right mouse button clicks with 2 additional LEDs. It's just a quick demo of the device as it's working pretty early in its development. If it fires up here for me, you can do it. You can see here that we initially built this 4-tiled system to do some initial prototyping. Let me see if I click this here, if it'll start for me. It's supposed to just go on its own. No, that's too bad. I guess we're not going to see this. That's a shame. Basically, I was just going to show quickly how it's calibrated and then the device tracking around on the table. You saw there, of course, that there are these borders in between the screens, and that is a current limitation of this technology. We're dealing with that right now by explicitly hiding the pixels that would normally be drawn underneath those borders. And what that does is it sort of gives you an effect of looking through sort of like a set of windows. Underneath, the image seems to be a contiguous image. Straight lines, of course, stay straight, which is a problem if we didn't do that. So we've developed a few applications so far to test this system. I won't go into the FITS validation application in too much detail. Basically, we heard a little bit about FITS law earlier, and using that 4-tiled system, we've sort of mocked up a simple application which does target acquisition, varying the sizes of targets and varying their distance. And our initial sort of interaction with that device leads us to believe that this is indeed a FITS device, which means that the interaction with this device is natural in a sense that it's similar to, for example, a mouse, which is also another FITS device, which exhibits sort of a natural and expected behavior. Some of the other applications that we've developed, the Galaxy application here, you can see just a quick screenshot of it on the left. We rendered the Hipparcos and Tycho data sets, and this application has sort of given us a first look at user interaction on this table using the tracking system. And basically, it's a first-person fly-through. It's sort of fun. But that has been a very encouraging application for us, because as we interact with it, we notice that really those borders seem to sort of just sort of fade into the background as you become more involved in the application and more immersed in the interaction. And secondly, we're working on a map application right now, which basically maps out a graphical map. I don't want to say like Google Maps. I'll say like MapQuest maps. And with this, we've just started working with panning and rotating the map around, and we intend to continue to use this application to look at some other types of interaction. For example, we want to try testing a lens type physical interactive device, which will allow us to do things like overlay regions of satellite information on top of the graphical map. Concurrently in the lab, we're working on this large display tiled LCD technology. We recently unveiled the LambdaTable, or got it functional pretty much. And using a common display manager that we developed called SAGE, the Scalable Adaptive Graphics Environment, we are starting to look at paradigms for developing an integrated project room based on this tiled display technology. So the idea is to put the table here in the foreground and look at things like using the table as a way to interact with detailed information for which the context information is displayed on the wall, or using the map as an overview and being able to highlight regions for display in different areas on the wall. So in order to sort of talk about what the potential benefits of this system are, we have two example scenarios here: the Terabyte Imagery Workbench and a multi-sensor situation table. The Terabyte Imagery Workbench is more or less a solution for the initial problem that I posed here with these large images. And basically, this is a tool for allowing scientists to display a number of these images on the display at once, start working with these images using physical interactive devices like physical markers or this lens concept that I talked about. We want to be able to lay these maps or these images out and spread them around the table and be able to stack them and start using them to try and build correlations and relationships between these different data sets. Once again, these data sets are very high resolution, so we're taking advantage of this high resolution display in order to be able to do real functional work with these images. In addition, just some other examples of type of interactions that we're looking to facilitate. Once again, correlations between, for example, cores from geographically separated sites, or being able to mark these sort of fiduciary points or confidence points between the core data with tangible interface markers. Also highlighting or extracting regions within these images directly on the table, directly on the images. So for example, for the guys at NCMIR, they have stacks of data which represent scans at different layers, and with that data they're highlighting regions in that data and using it to build a three-dimensional model of the scan that they've taken. And that's a very tedious process. Actually, it takes months using just a mouse and a display. So with this, we're looking for some ways to facilitate that process so that the users can interact directly on the table. And then finally, embedding metadata and comments directly on these different images so that they can share, to share that data so that another user that comes up and looks at that same image can see that metadata directly within the image. And in terms of the collaboration aspect of this, because we have this high resolution display, we can start looking at doing some interesting things with developing sort of personal or multiple individual user workspaces on a table. We can spread out the data into different separate workspace areas. orienting that data correctly for each user using sort of like a physical workspace icon that they can place near them and orient correctly, and use that to sort of create a persistent workspace on this table. The bulb life of an LCD monitor is quite long, so we could technically use this display at any time, leave it up, and users can come in and out of the space, work on their little workspace, and leave, and not necessarily have to restart the application every time. And finally, with this high resolution, things like text, when rotated, will still be legible. The second example is this multi-sensor situation table. I actually just got out of the Navy, so I'm drawing on some of my experience there. I spent 4 years as a naval officer, and we used a lot of systems on board to sort of share a mutual picture of the tactical scenario. So, and a device like this could be very useful for something like that. The concept is for, not just military, but perhaps emergency response workers or, for example, airport ground controllers, to be able to share this map information, multiple sensor data, high resolution, high definition video, or satellite volumetric data, whatever it is that the data that's involved in their control environment, and be able to share this big picture without sacrificing the important detail that's inherently involved in these situation environments. In this environment, they could use these tangible markers to do things like identify status information for infrastructure in the environment. Put a marker directly on a runway that says this runway is currently snowed out, or this one just had a fire. Also designate regions of interest that then could be displayed on the wall for other people working in the project room. And also generally provide sort of these obviously recognizable points with which to sort of facilitate the acquisition of common ground amongst the people that are working. So as opposed to a lot of dialogue back and forth as to, this contact bearing, 320, which contact is that? There's 2 along that bearing. Well, in this case, you could say, the red marker, I got a contact right next to that marker, something to that effect. And once again, using specialized physical devices like the lens that I talked about, we can use that to start laying on top of the graphical information sources like satellite imagery and video imagery. And once again, because of the bulb life of the LCDs, these devices can be left on at all times, allowing them to be always ready in case of an emergency. So in our effort to make these a reality, we're progressing right now. Right now I am working very hard building these tangible user interface devices, and we intend to have done here an application to start working with images on the table and to start looking at these infrared reflectors this fall. By the end of this academic year, we expect to have this device integrated with the Sage system so we can start looking at these project room paradigms. And also, we're going to continue to we expect to have this FITS paper out separately shortly, and also start to compare some other interaction with human subjects. And beyond that, we're looking at tiling the cameras to improve the user interface resolution of the tracker, and also to look at building some toolkits for things like multiple inputs on a single display, also this concept of oriented multi-workspaces around the table. And that's pretty much it for me. This device was developed with funding from NSF and also ONR. Unfortunately, I am not funded. Another thing I learned is not to be shy as a grad student for asking for handouts. So, oops, I throw my contact information up there. And that's it. The website's on the way. Thank you very much. Yes?
Say something about why you chose to use a table. I can understand that maybe for tangible bits it has gravity.
Mm-hmm.
They could be electronic. The trouble with tables is people standing around at different sides have to be oriented if there's no consistent down and up.
Right, so one of the things we're trying to do with these, I think I mentioned something about a physical icon for a workspace. So because I can track orientation with the tracking system, we're going to try and experiment with orienting positions around the table for a user that's standing there by using sort of an orientation physical icon.
Or does each person see a portion of the table with their orientation?
Well, I suppose it depends on what kind of data is on the table. In this case where we have a lot of images and people are each working on a set of images, those images can be oriented for that particular user. In the case where the data is general, we can start looking at, for example, if somebody's using the device, he might have a marker that would orient things in his region to face him. These are all things that are definitely great questions. So we're continuing to look at that. Any other questions? Yes? I'm sorry, say again?
Bezel-less monitors? So there's a monitor that's
right. We've been...
Yeah, I have much smaller. Oh, they make some that are thin. Well, yeah.
One of the things that we are trying to do is to use devices that are cheap. That's sort of part of the strategy, is to come up with not too expensive solutions. Also, we are using, in some of our systems, a relatively small border around the smallest that we could get. But once again, we're using a lot of commodity products to try and make this affordable and functional. There are some technologies that hopefully will eliminate the borders altogether. Organic LEDs, we're hoping will continue to become cheaper and larger so that we can start potentially employing that. And also there are systems, optical, for example, like an optic lens type device that can be placed over the table and spread the image out so that you basically eliminate those seams. But we found that so far in our interaction, even with the borders, we're still able to do a lot of interesting research, and it hasn't, or at least we've been encouraged by the still quite functional and easy to use aspects of the device. So.
Did you say with the table, are you setting anything on top of it, like a glass spanning the whole thing, or?
Yes, definitely. We have like a plexiglass sheet right now that's over the table.
Does the distance between the top surface of the glass and then the lower surface of the LCD cause fraud?
It's something that we're continuing to look at. So far, with the applications we've done, it hasn't created a large problem, but I can definitely see, for example, in the future for certain types of tasks that becoming a problem. So we're looking at that.
Just to follow up on that, we have a plasma display, but in the case of a plexiglass cover, and the parallax on that is quite large, and it's definitely a problem.
Okay, interesting.
We played that for ours on the rear projection, and we used to do the diffuser on the bottom of the plexiglass. So you had that much, and when you put objects and stuff, you could definitely tell.
Right.
So we ended up turning it the other way with the diffuser on the top and then armor coated, so you didn't have the parallax problem. So yeah, it does come to play.
That's interesting. All right, well, thank you very much.